So, welcome everyone. My name is Mark Richter, and I'm an electrical engineer here at Powerside, who's together with a team put this little ATS demo together. So let's go over the specifications of the ASCO 7000 and what we actually have here. An ASCO 7000 is often used wherever critical power must be maintained. It can switch between the utility and an emergency power source, such as a generator or, for example, a Tesla Powerwall. The one we have here, it's got a couple of LEDs on the front here. Green signifies utility and red signifies emergency. We've modified it a little bit so we can turn on utility and generators like two control switches on the side. Also added to this ATS, we have the PQube 3E, Power Quality Analyzer, which is sitting inside here and is configured to what we have here on the wall. We are monitoring the voltage coming out towards your loads, and with CTs, the power going to your loads. But in addition to that, because the PQube has 14 current inputs, we also have CTs on the utility side to see how much energy we pull from the utility, and on the generator side to see how much power we pull from our emergency power source. I want to do two simple demonstrations today to demonstrate how quick this ASCO power switch can transfer. We're going to do a manual transfer from utility to the generator, then back. And the ATS should be able to do that with a 50 milliseconds transfer time. And then we're going to simulate loss of utility. And this ATS has been programmed to transfer in about 1.3 seconds. Before we get started, we need to start off and make sure we have our emergency source. We now have an emergency source. So the first test by the controller here, we're going to switch from utility to emergency and then back. You may have seen the lights flicker. They are one of our three critical loads here on the front of our ATS, modified it a little. We have a three-phase connection to a motor, and we have lights and a computer, a secondary load. The computer being our critical load. We did see this time around that the computer remained up. Everything seems to be fine. So let's go and have a look at those waveforms on the PQube. The PQube itself has a built-in web server. There is no third-party software or applications you need to load. And if we go to the web page, as we can see, we can actually see the meters page, which shows the voltages, the currents, and our load current right here. This is actually going to our loads right now. L6, 7, and 8 is actually our generator. And that, 6, 7, and 8 is the utility. 9, 10, and 11 is the generator. We have no power coming from the generator right now because we're actually running on utility. If we come further down on this meters page, we can see energy and power, how much is actually being drawn by our load, and via tabs we can see how much kilowatt hours is being pulled from the utility and the generator. Other interesting power parameters such as power factor, how much reactive power, energy, peak currents, as well as Class A data such as flicker, superharmonics, THD, TDD, and we have a list of harmonics up to the 17th on the web page. The PQube itself will actually tell you harmonics up to the 50th. So let's go and take a look at that transfer. So this is what we have here. We have a voltage sag that lasted 50 milliseconds. That's the transfer time of this ATS. So far, it's looking good. On the left, we have utility power. In the center section between these sags is where the generator operating, and then we went back to the utility. Everything seems to be in order here. If we scroll down slightly, we can take a look at the load current on L1, 2, and 3. And we can see the load current more or less remain consistent with these two inrush currents right here at the time of transfer. to the generator and back to the utility. Towards the bottom of the screen, we can actually see what happened. We have our utility and we have our generator. At the time we lost utility, the generator picks up, and when we switch back from the generator, the utility picks up. Interesting thing we see here is we see a large amount of inrush current. With the PQube sampling capability of 512 samples per cycle, we're really able to get detailed on these inrush events, as well as show all the waveforms simultaneously at the same time, as every channel is sampled at the same time. Moving on to the waveform, we see the same information at the top. We have 5% remaining voltage, and the sag lasted 50 milliseconds. This is the start of our sag. It happened exactly 9 and 14 seconds. And we can see at the very beginning of the sag, there was a very nasty let go from the utility, an equally nasty reconnection to the generator. Very abrupt, very straight lines here are a sign of high frequency components. If we scroll down a little bit, we can actually see our loads were disconnected. Zero current was flowing for the duration of 50 milliseconds. And further down, we can see utility now is zero. But very interestingly, on the generator, we see like this Christmas tree shape. This is actually the charging and firing of the ATS solenoid. If you see a change in the shape there, your solenoid is in trouble. Or if it increases in current, perhaps the mechanics of your ATS need greasing or servicing. And then we switch onto the generator, and our loads pick up and life continues. So our next test, we're going to do our design transfer time of 1.3 seconds. You may want to increase transfer time to minimize inrush of reactive loads. So we have our generator running, and I'm going to lose our utility. Here we go. A little bit more drastic that time. 1.3 seconds is a long time electrically. Transfer switch did its job. You saw the lights disappear. Our rotational load here to the right actually stopped, but it picked up again. And we had failure of our critical load, our computer system. So let's go and take a look of how long it took to transfer to see if we were in our 1.3 second specification. Right there, we have a voltage interruption of 1.268. I think we can call that 1.3 seconds, and there it is. That's when our interruption happened and for the duration. And we can see it on line to line, line to neutral. And if we scroll down, we can actually see we had loss of power to our loads. L1 to L3 is on the output of the UPS, of the ATS. Coming further down, we should be able to see we lost our utility, which is on 6, 7, and 8. But the generator picked it up on 9, 10, 11. So at this stage, we're actually seeing some interesting times, and it appears that our ATS is performing well. We did get some strange squiggles here. I actually think this is a motor restarting on the right here. But everything is back up and running. Things are great. Let's look at the waveform. If the event lasts longer than 500 milliseconds, the PQube actually captures the beginning of the event and the end. So you get this blue chevron line down the center of the page. That's just wasted time where nothing can happen. As before, we see the length of our voltage sag, 1.3 to spec. A very nasty let go here. And a nasty it picks up again, poorly here. Scrolling down the screen, as everything is sampled simultaneously, we can see loss of flow to our load, our inrush current, which is almost 500% of the actual load. And further down the bottom, we have loss of utility, and this one, charging of the solenoid, and now we're on the generator. We're up and running. So everything seems to be fine, or is it? The PQube has a dedicated 4 megahertz sampling processor, which actually is capable of looking at supraharmonics, things up to 150 kilohertz. These spikes and transients occur at sudden switch on or switch off. And here, can we scroll down just a little bit? We can actually see our sudden switch back on. And at this point, the PQube detects a high frequency transient. These transients can actually travel really quickly through your electrical system, damaging insulation, causing higher currents to flow, damaging transformers, and generally degrading the life of electrical equipment. Things like our little computer here have detection circuits on the inputs of power supplies and rectification and capacitors, which all see this spike of current and voltage and is degrading to their health. Our very small system here has very little energy. At the top of the screen, we can see that we basically detected zero energy in this transfer. It is very small. However, in larger systems where your ATS may be running at hundreds or 1,000 amps or more, this can be a very significant event and cause things to stop working. With the use of a PQube, you should be able to correlate the failure of equipment with what happened. But why are we seeing these high frequency transients on this transfer switch? Well, this is an old transfer switch, and I happen to know that the contacts on 2 of the phases could do with replacing. And you see that when we disconnect and reconnect on the transfer switch, those rough, noisy edges of the voltage waveform. And this actually causes voltage to start and stop and this high frequency transient. So what have we learned here today? With the addition of our little PQube into this ATS, we're able to show a few things which happen. We did a manual transfer of our ATS, which you can program the ATS to do on a monthly or weekly basis. And we can actually track the transfer time to see if it transferred at the speed it should. Degradation in this would show that your mechanism or mechanics needs servicing. We can see that it worked at its maximum speed of 50 milliseconds, and it actually transferred as our program speed of 1.3 seconds. This also verified that every phase was transferred, not just L1. With the PQube's capability of sampling of 512 samples per second, we're able to see this transfer very clearly, both voltage and current. An also useful parameter is because we're monitoring the utility and the emergency power separately, we can see how long the generator ran for and how much kWh was being pulled. Useful if you have an increasing size of a data center, you might be aware that you're encroaching on a power limit. Or if you have to log how long your generator ran for. This is all done for you inside the PQube. All wasn't quite well today with our demo. We noticed that we had some high frequency transients coming from the transfer from utility to generator and then back again. This could, over time, damage sensitive components and power supplies, thus damaging maybe a UPS or a computer or a server system further on your system. Getting all this data couldn't be easier from the PQube. The PQube 3E and family has a built-in web server and FTP server. It automatically plots each graph for you. All you need to know is the IP address of the PQube. Point that address, and you can see all the waveforms we showed this morning. As quick as that. All 14 channels and both current and voltages are simultaneously sampled. You see them all in one GIF image, so you can see what happened and how long it took. If you have a facilities manager or a plant engineer, the PQube can also be programmed to email them directly, or a number of people. So when an event occurs, a PQube will be sent to your plant engineer showing that you're now on emergency power and this is how long it took to transfer it straight into his email box. Keeping logs of these emails is keeping track of your ATS, seeing an increase in transfer time over time, or increased inrush currents, or poor transfers can indicate that maybe it's time to start your ATS maintenance and not wait until the lights go out. Any more questions about the PQube, you can contact us here at PowerSide.